This is my code for LAB04, driving the Romeo robot forward and backwards, relying on the encoders to speed up and slow down our motor wheel. So, real quickly, we have our libraries, we have our static variables. I found my wheel diameter to be closer to 6.95. This also helped me more reliably get to 100 centimeters. As we said early, the pulses 1437 per wheel turn. Difference is just the number between the right and left pulse, and we'll see that later on in this code. Motor delay I've set to 0. That's just that was a delay I used to possibly when the motors change speed, to keep it less choppy. I experimented with delays. It didn't really help, so I'm just setting it to 0. Also within the code, I'm setting a max speed of 254 pulses and a minimum of 24, and I'll cover that a little later when we get down to the function it refers to. Our dynamic variables, they're the same, except right now for the purpose of this video and demonstration, I'm setting my left and right motor speeds at 40 pulses. Other than the main requirements for this lab were, of course, to drive 100 centimeters forward and backwards and see how we do compared to these deviations. Speed wasn't really defined for us, so I'm going to keep it at 40. In our setup, of course, we're setting the baud rate at 9600. In our loop function, we're calling two functions here. We're calling the button press, which is straight from the example provided for us. The drive straight is also in the example, but this is where I did most of my modifications. Button press, again, same as before. I won't go too much into that, but it gets the encoder. It resets the left and right encoder counts. Let's see. We also get the number of pulses, and that's also calculated from the function below that was done for us, taking wheel diameter, counts per revolution, and distance. So into our drive straight function. It can either go forward or backwards depending on whether A or C button is pressed. So once it's pressed, the encoder, the microcontroller gets the left and right encoder counts, which we had set to 0. It also sets the motor speeds to the initial motor speeds of 40, left speed and right speed. And remember we said earlier that I set the difference to 0, the difference between the left and right pulse count. So for the purpose of this, I'm basically saying if the left count is less than the right count, I'm going to speed up my motor. However, I'm not going to go higher than 254 as I stated above to protect the motor. So it can keep incrementing in this way. If I had longer distance, it would never go over 254. It really reads 255, but it won't go over that. Likewise, if the left motor count is higher, the left encoder count is higher than the right encoder count, it will decrease the speed, and it won't go lower than 24, or I believe I set for this, because if it keeps going low, it will just reverse direction. So I stopped it at 24, and we really don't need to go lower than that anyway. It basically stops moving at that point. We're also printing the pulse counts, and we're also going to print the left motor speed and the right motor speed. And I can show you that in a second. We have, if button C is pressed, we will get the encoder count. It'll set the left and right speeds, but it'll set it in we're defining as the backwards direction. And this is a little counterintuitive. Since our pulses are being read as negative, you have to look at it this way. If the left pulse is greater than the right pulse plus the difference is 0, we will speed up the motor. Again, max speed will be 255. And then it will send it in the reverse direction. if the left pulse is less, and again, less, also counting the negative sign, is less than the right, it will decrement or decrease the speed. Again, not going below 24, because that would just send it in the opposite direction. And we are printing the, again, we're printing the pulse count, and we're also printing the speeds of the motor. Here is our roaming robot. What I will do, I removed the front caster. I'm not weighting it. I feel at 40 pulses, I don't need it. At the higher pulses, I do. But for the purpose of this, I'm not going to weight it. I'm going to upload the code. It's uploaded. Before we do a demonstration, I'll show you what's going on with the serial monitor. And I'm using a different sketch here for the serial monitor, but let me reset this. So if we press the A button, sometimes you have to keep pressing it. Or I have to hold down the button. And you can see the wheel skipping, and you can see what's happening here. If here we'll wait till it stops. It's kind of hard to read when it's moving like that. It'll be over in just a second. A little longer than I thought. Okay, so I won't go through all of it, but for instance, you can see like here, when I'm scrolling, let me make sure I can get a good picture. When the left pulse is less, let's look right here. Let me stop it from scrolling. Okay, so let's look at here. Okay, having trouble showing this. Oh, it's still scrolling. Okay, basically when the motor pulse is higher on the left side, it's gonna slow down the motor, and you can see the speeds here, and it will only go down, well, 23. I said at 24, but it goes to 23. That's the lowest it will go. And let's see up here, slowing down the motor, slowing down, and then when the left pulse falls below, as you can see here, it fell below, it will speed up the left motor. Okay, so we saw all of that. Once again, this is my track. And let me make sure I can get everything here. It's 100 centimeters, and I have the left and right sides noted. Helps with our measurements here. I'm going to put toothpicks on the front and back. Just helps with visuals here when we do our measurements. Let me just make sure they're straight. Otherwise, our measurements will look a little off. It's good enough. So I will align this up. Should also be noted that you can't tell it from the video, but my straight line here is not exactly straight. I've noticed that throughout testing. I'll have to have proper tools to get that straight. All right. Without further ado, I'm going to press the button, and we're going to go straight. Let me make sure. Here we go. So it's a little choppy just due to the motor turning off and on. If I had more time, I would try to have a smoother transition. But it's fairly straight. And almost stops exactly where it needs to stop. We'll take a look at it here. So real quick, I will use this is at 15 millimeters or 1.5 centimeters. So at the front, it's pretty dead on. We'll just measure it from the back here. From here to center, it's definitely within the deviation, so good on that. The wheels here, looks like it's off by definitely less, maybe less than a centimeter on that side. This side, pretty much the same, less than a centimeter. Definitely within the range here. So. To the rubric, it would be excellent, excellent range. So we're going to move backwards. Let's see here, make sure I can capture everything. There we go. So we're going to go backwards here, make sure everything's ready. Hit the C button. Sometimes it's a little finicky. There we go. Again, the motor's a little, I don't like the choppiness of the left motor, but for the purpose of this lab, it fulfills the requirements. And pretty good stop here. So we'll take a quick measurement here. So here's our 1.5 centimeters, and I'm within that. We can look at it here. Also within that as well. The wheels, this side dead on. Right at 100 centimeters, and pretty much right at 100 centimeters on the line. So according to the rubric, this should be, I would say this is excellent results.